Good morning, everyone. Today I'm presenting a short summary of transport phenomena diffusion reaction problems. This presentation covers diffusion in liquid phase, catalyst for diffusion, and spherical diffusion. The aim is to understand how mass transfer and reaction combine in different geometries. The first problem here, the gas A dissolves into liquid B and reacts to form AB. We assume steady state and no convention and pseudo binary diffusion in this case. So using shell balance approach, we obtain the differential equation as DAB d2Ca upon dz square minus Kca equal to 0. And the boundary conditions are fixed, concentration at the interface and zero flux at the bottom wall. Next. Now we are again we are defining theta as the dimensionless form. To simplify the equation, we define the dimensionless variables as theta and xi. This introduces the Thiele modulus, which compares the reaction rate with diffusion rate. As we know, Thiele modulus equal to root over KL square upon DAB. The final ODE becomes as a d2 theta upon d psi square equal to uh, Thiele modulus square into theta. Now the final concentration profile becomes theta equal to cos h Thiele modulus into 1 minus xi upon cos h of Thiele modulus. This shows that higher Thiele modulus causes sharper concentration decay. In question number 1, this question is based on cylindrical catalyst pore. Here reactant A diffuses through a long cylindrical catalyst pore with a zero order wall reaction. Using cell balance, the concentration profile becomes parabolic. We get the final expression as Ca of x equal to Ca naught minus K upon dr into 2 into Lx minus x square. From this, we also derive the minimum pore length required for complete conversion. In next question, this question is based on diffusion from sphere. In this case, the species of A diffuses radially outwards from a sphere. The steady radial diffusion into stagnant fluid. At steady state, the total molar flow remains constant across a spherical surface. The flux follows inverse square behavior. That is flux is inversely proportional to 1 upon r square. This means that as the radius increases, the same flux spreads over larger area, so flux decreases. By using the condition given in the question as r equal to 10 centimeter, we get the flux equation of P as a 2000 upon r square, which gives us 80 mole upon centimeter square second. In next question, it is based on spherical shell and the diffusion through stagnant B. This problem extends spherical diffusion through a shell into stagnant B. Applying shell balance and Stephen diffusion equation, it gives the molar rate expression between the two radii. The important idea here is that spherical geometry introduces radius dependent area changes, making the derivation different from the planar systems. By shell balance, we get the equation as d upon dr of r square into Na equal to 0. And the total molar flow rate we get as Wa. In next question, this question is based on porous plug with first order reaction. In this problem, the liquid flows upward through a porous plug of A. Here, A dissolves and reacts by first order reaction. So in this case, we have axial convection and diffusion, and also reaction also taking place. So the governing ODE becomes as DAB into D2CA upon DZ square minus V naught DCA by DZ minus K double dash into CA equal to 0. This includes the diffusion, convection, and reaction together. Here we get the boundary conditions as CA at Z equal to 0 as CA naught, and we are taking CA naught at infinity distance to be as 0. Next, for getting final axial concentration profile, we are using exponential trial solution to solve the characteristic equation and keep only the negative root to satisfy the infinite boundary condition. The final concentration profile we get is the exponent of m minus z. That is Ca upon Ca naught equal to exponent e to the power of m minus z. This shows the exponential decay of concentration along axial direction. As we know, we already got the characteristic equation as dAb into m square minus v naught m minus k double dash is equal to 0. So the main learning points from this assignment are shell balance and equation of change gives us the same result. For complex examples, we use equation of change for the simple solutions. And here Thiele modulus helps us compare diffusion and reaction, which dominates more. And we use dimensionless groups to simplify the sums and simplify the interpretation of this example, and we can easily solve the question. And geometry can strongly change the flux profile, and boundary conditions are very important in solving the constants. To sum it up, this assignment covers planar, cylindrical, and spherical diffusion systems. It shows how reaction and diffusion interact in different geometries. These derivations are very useful in mass transfer, catalyst design, and transport phenomena. Thank you.